22, they say, according to a survey, 86% of all adults in the United States think that the U.S. government system is broken. And I usually just write down some notes for myself so I don't have to keep looking back at the book. 86% think that our government is broken. Of these 86%, about 8 out of 10 think it can be fixed. So of these 86, 8 out of 10 think it can be fixed. First one, find the probability that the randomly selected adult thinks that the U.S. government is broken and thinks the government can be fixed. So we want the probability that they think it's broken and they think it can be fixed. Well, to do that, what you have to do is use the multiplication rule. What's the probability that we pick somebody that thinks it's broken? 0.86. And the multiplication rule says that we take these two and we multiply them together. So 0.86. Now the people that think it can be fixed is 8 out of 10. What's that as a decimal? 0.8. Grab your calculator and help me out. What's 0.86 times 0.8? Say it again. So that's the probability that we pick somebody who, first of all, thinks it's broken. So we're picking from that group that thinks it's broken. What percentage of the people in the U.S. don't think it's broken? All right, if there's 86%, what percent doesn't think? 14% thinks it's not broken. I don't know that we need that for this problem, but so out of the 86, we pick, we're picking somebody out of that group that thinks it can be fixed, which is 8 out of 10, 80%, and we come up with 0.688. Somebody help me out. What's part B say? So I don't have to keep reading out the book.
Given that a randomly selected adult thinks the U.S. government system is broken.
All right, stop right there. So we're picking out of just the people that are broken. We're not picking out of the whole U.S., just the people who think it's broken. All right.
Find the probability that he or she thinks the government cannot be fixed.
So broken and not fixed. It's not possible to fix it. We think that we're just going downhill and the government's going to collapse at some point. Again, what's the probability that we're picking from? 0.86 times what's the probability that it can't be fixed, or that the people think that it can't be fixed. Instead of 8 out of 10, what's it going to be? 2 out of 10, which is 0.2. Multiply those two together, what do you get?
0.048.
Is that right? Yeah, I don't know that I did it right. I'm trying to think here. Broken and can fix it.
Oh no, I thought it said the government system. Never mind, I did it wrong.
Let's see here if I did this right though. Broken and can be fixed.
I did 0.24.
Broken and can't be fixed. What should be true about these two? They should be the complements of each other, right? So instead of doing all that, what could we just do with this number? 1 minus 0.688, I think. Somebody do that for me. trustworthy, right? I give you that book earlier this year.
Yep.
Let's make sure I'm right before we go on. So if we had that, let's see what I was gonna do. Somebody help me out and tell me what was 0.86 times 0.2. If we were gonna do it that way.
We'll do it wrong. It says n equals 20. This is confusing.
You on the right page?
Yeah, I think so.
Section 3.2. You're in chapter 4. Yeah, probably doesn't look right for that problem. It's gonna be back quite a ways.
I thought they were the same page.
There's chapter 3. Say do it this way.
Yep.
So broken and not fixed, all we do is take the complement of what we said. Up here we said broken and fix. Well, if one person thinks it's broken and you can fix it, then the rest of the people are gonna think that it's broken and you can't fix it, right?
Actually, they did 1 minus 0.8 equals 0.2.
And then did they go on down?
No, that was the last thing they did.
I don't see
I think
It says the formula and then it says 1
That is-
minus.
I think it is because what did they just do the complement of 0.8 since that's.
Alright, so these are the people that say, these are the people that think that it can't be fixed.
So what did they do, like the 1 minus?
So it'd just be 1 minus 0.8, which is 0.2. That should be the right answer. I even had it right on my paper, didn't I, Sean? So on my homework, I did it right, and then I'm trying not to look at it to make sure that I remember how to do it still. So, let's go back over this, just real quick. Broken, and you can fix it. You take the 8.86 times the 0.8, that's gonna give you the percentage. We did that one right?
Yeah, we did that one right.
Alright, so that's that. Then they wanted broken and cannot fix. Well, we're deciding from these people whether we're 8 out of 10, well, how many people think that it can't be fixed then?
I thought that was people that
Just
thought it could be.
2 out of 10, right? This is 8 out of 10 thinks that you can fix it.
Oh, 'cause everyone thinks
So-
all those think it's broken.
Right. So 2 out of 10, 2 out of every 10 people is gonna think that you can't fix it out of this whole 86. So we didn't need to do a multiplying or anything. We took the complement of this, which would be broken and can fix, which would mean the complement of that would be all the people who think it's broken and you can't fix it, and the people who think that it's not broken at all. So we found the percentage of those people who were, so if we were making a Venn diagram, and these are the people that think it's broken, this is broken, well, some people think that you can fix it, and some people think that you can't fix it. And then all these other people out here think that it's not broken. Well, some of them think you can fix it, and some of them think that you can't fix it. So what we found when we found this, we found broken and fixed, that's this little part right here. What we found when we found the complement, which our numbers don't fit my picture, but we found everybody else, which they didn't ask us for. What's part C say? Would it be unusual for a randomly, that's wrong for Would it be unusual for, yeah, I was looking at the one above it. Selected adult in the government system is broken and think the government can be fixed. So, can be fixed. That was, can be fixed. So we're looking at this percentage right here. Is that unusual? What's a percentage gotta be for it to be considered unusual? 5% or 0.05 or less? Or 95% or higher? Is this either one of those? So this is not unusual. Not unusual.
Not unusual.
Right. Because to be unusual, it's gotta be 5% or less or 95% or higher. Other questions? That there was fairly easy, if I wouldn't have screwed it all up there. Should have looked at my homework instead of just trying to do it off the top of my head. Yeah. Here, I'll help you look at yours.
Oh, thanks.
Just ask me if you need to see it again. Other questions?
Answer to
42, I remember this one. I was getting tired. Couldn't read it. By rewriting the formula for the multiplication rule, you can write a formula for finding conditional probabilities. The conditional probability of event B occurring given that event A has occurred. And they give us this formula. So you guys gonna help me out with this, right?
Of course.
And not laugh at me if I mess it up.
What are you reading?
42, the directions above 42.
Oh, okay.
So they give us this formula, probability B, given that A's already occurred, equals the probability of A and B. So the probability that both of them happen, and are divided by the probability that A happens. They tell us probability that an airplane flight departs on time is 89%. So I'm just gonna write over here, on time, 0.89. Probability that arrives on time, oops, let's put departs here. Arrives on time is what, 0.87, is that what it said?
Yeah.
And the probability that it does both is 0.83. So 83% of the time, the plane leaves on time and gets there on time. 89% of the time, it leaves on time. 87% of the time, the planes at this certain airport, wherever, arrive on time at their destination. 42 says probability of flight arrives on time given it departed on time. So we want probability that arrives on time given that it departs on time. So arrives on time, arrives, taken from the fact that it departed on time. So A or B given that A's already occurred. Arrives on time, departed on time. So we want A to be probability that it departed on time. What's the probability that our planes depart on time?
89.
So we're gonna put 0.89 on top. Since this is A and B, we're gonna take that times the B. What's the probability that arrives on time?
It's
0.87. And this time we want the B to be probability that arrives on time given it, so we want it to be arrives on time. So we divide by 0.87 goes on the bottom. So probability of A, probability of B, probability of B, or A, sorry, not B. I got these two backwards, but that doesn't really matter. Somebody do that on their calculator and tell me what you get out of all of that. 0.89 times 0.87 it equals, and then divide it by 0.87. 0.89. So if, let's go back and explain this. If we know our plane departed on time, we left on time. So we were taken off from the airport and we flew out right on time. What's the probability that we're going to get to our destination on time? 89%. That's what it says in there.
That's not the answer, no.
Really?
Well, they divided it, never mind, it's pretty much the same.
Oh, no, I did do it wrong. Because this top should be, be
0.83.
0.83, both of them. Because that's what it said, what,
I'll do that.
should've told me.
Well, I did. I see my homework review.
So what's that give us? 0.83 divided by 0.87.
0.89.
I should have done that. A and B is this, right? Both of them occurred. That was just ignorance.
The bottom number on here is 0.89. 0.87.
What is up with you today?
I'm looking at the next one. If I do another problem, I'm looking at what I did. Quit trying to guess. 0.93.
What is up with you today?
Trying to do it because I'm trying to learn also, make sure I know. And I shouldn't be.
So the only thing that we have to write down is that 0.83. Okay.
Other questions? I'm not missing the next one.
Are you looking at it?
I'm going to look at my homework.
What? Why?
I was wondering if that was.
I didn't even notice that, I always do that.
I
No, I didn't even realize I was doing it.
40. Problem 40. I don't think we did 40. We didn't do 40. Let's see if we can do 40. Class, 24 students, you want to find the probability that at least two of the students share the same birthday. Let's do 40. Even though we didn't do it, let's do 40. See if we can figure it out. So watch. And we'll do it for our class instead of doing what the book says, we'll do it for our class. We got 1, 2, 3, 4, 5, 6, 7,
13.
8, 9, 10 students in here. 4, 7, 10. So we got 10 students. We want to find the probability that at least 2 of you share the same birthday. So we want to find the probability that 2 students share a birthday. Well, to find this probability is going to be difficult, but what we can find is the probability that none of you share the same birthday. All right? And that's going to be fairly easy to find if none of you share the same birthday. If we're going to find that probability, what we do to find the probability that none of you share the same one, so we look at Dalton over there. What's the days that Dalton could have his birthday on? What out of what? How many days in a year? 365, that goes on bottom. All right. Now, is it just one? It's 360. Not 4. 5. Because right now we're starting. Does it matter what Dalton's birthday is? No. Because right now, is he going to share it with anybody else? No, because we haven't dealt with anybody else yet. All right, so 365 out of 365. Now, when we go to Carson, there's still 365 possible days that his birthday could be, but Dalton took one of them. And we want all the people, or we don't want you guys to share the same birthdays. So how many is here? 364. Next person, we go to Riley. Well, Dalton's took 1 day, Carson's took a day. Can Riley take either one of those days? No, because we want nobody to share the same birthday. So what's hers gonna be?
So what if there's two people each same birthday?
363 out of 365. Now, what would Jesse's probability be?
What if there's two people? with the same
362, 365. What would the next one be? Or what would Jacob's be? 361 out of 365. I want you guys to listen so you can understand this instead of talking so much. Next one's gonna be 360 out of 365. We got 1, 2, 3, 4, 5, 6. How many more do we need? So 359 out of 365. 358 out of 365. 357 out of 365. 356 out of 365. Is that all 10? Is that 10 of them?
Yeah.
So we got 10. Now, to answer Jesse's question, Jesse said, and I answered this at the beginning, but apparently you guys were there screwing around, so you weren't listening. Don't look at me that way, Jesse, because right now, do I look like I'm in a good mood anymore? No. The reason that we're not talking about somebody having the same birthday is because what we're actually trying to find is if two people share the same birthday. All right? What's the probability that 2 or more of you share the same birthday? Well, if we figure out what's the probability that none of you share the same birthday, then we can take that answer and subtract it from 1, and that'll tell us if 2 of you share a birthday, or 3 of you, or 4 of you, or maybe all 10 of you. But that'll tell us the complement of that, so it'll tell us all the other stuff that's left over. So if I'm looking at a Venn diagram, we have this. There's this little circle in here where none of you share the same birthday. That's what we're finding when we're finding this probability. Well, everything else is the probability that we actually want to find. If 1 or more, or 2 or more of you actually share a birthday. So we can find this probability, which is easier to find than trying to find if 2 of you share a birthday, or if 3 of you share a birthday, or if 4 of you share a birthday, or 5 of you share a birthday, so on, so on, so on. All right? So we can find this and then just subtract from 1. Now this isn't going to be an easy one to find. Somebody help me out and multiply all these top numbers. 365 times 364 times, and I'll write down that number here in a second, and I'll find the bottom number.
Oh,
It's going to be a big number.
geez. Not such thing as big numbers.
You might want to make sure that you're doing this on your calculator so you can see what we're talking about when we get this answer, because you're going to get answers like this and you're going to have to know how to write them. See, I hear Sean over here going, because he doesn't understand what it means.
You can't remember this, like, the scientific notation.
It's in scientific notation, isn't it? So somebody tell me, what is the scientific notation?
3.7162.
Close. So 7.2 will say, and then what's the E part say? 10 to the 25th. And that's what it means. It means 3.725 times 10 to the 25th power. And what that 25th power is telling us is that we got to move that decimal over that way 25 times. All right? Now my number, when I did the bottom, came out this. 4.197 times 10 to the 25th. So if you're on your calculator, you got to know that that E is telling you scientific notation. It's telling you times 10 to whatever that number after the E is as a power. Well, if I'm looking at this, all right, what's going to happen with these 10 to the 25th powers right here? They can just cancel out. So all we end up with is 3.72 over 4.197. Somebody divide that on their calculator for me. Say it again. 0.8863. Now what that's saying is that we have about an 89% chance, if we went through and I asked you all of your birthdays, that none of you would have the same birthday. About 89% chance. Does that make sense? Yeah, it's probably pretty likely that none of you are going to have the same birthday when there's only 10 of you, right? That's not the answer we wanted to. What do we got to do with that number? Subtract it from 1. We wanted to know what's the probability that 2 of you do have the same birthday. So what's that? 1137. It's about 11% chance. So if I went through and asked all of you your birthdays, there'd be about 11% chance that 2 or 3 or 4 or 5 or 6 of you would tell me that your birthdays are all June 5th or something. Does that make any sense? That's 11% doesn't seem like is that an unusual? Would it be unusual then if we went through here and 2 of you had the same birthday? No, because that'd have to be 5% or less, right? If we had fewer people in here, then the percentage would go down. If we had more people in here, then there'd be a better chance that 2 or 3 or 4 of you would have the same birthday. Again, to find the probability that if we wanted to do it the long way, the probability that any 2 or 3 or 4 of you share a birthday, then what we'd have to do is we'd have to go through and find the probability that 2 of you share a birthday, plus the probability that 3 of you share a birthday, plus the probability that 4 of you share a birthday, plus the probability that 5 of you share a birthday, so on, so on, so on, all the way up through 10. We'd have to find all those probabilities separately. Do we really want to do that? No, that's a lot of work. The easier way, find the probability that none of you share a birthday, and then just subtract that from 1 because it's the complement. How would we find the probability that exactly 2 of you share a birthday? That there's exactly 2 people in here that share a birthday. We do the same thing, right? Let's say Dalton and Carson again. What's probability, or what's Dalton's probability for his days that he could choose from? 365 out of 365 times. Now here's where you got to be careful, because when we go to Carson, this time we don't want Carson to have a different birthday. We want him to have the same birthday. So instead of 364 out of 365, 1 out of 365, because whatever day Dalton's was, that's the only day that Carson can pick if we want them to be the same. So that'd be 365 over 365 times 365, which is going to reduce to 1. Somebody help me out. What's 1 divided by 365? So the probability that 2 of you in here have the same birthday is less than 1%. All right, and if we did that for 3, for 4, for 5, for 6, for 7, so on and so on, they're all going to add up to that 11%. All right, go ahead and write this down. Addition rule. That's what we're going to cover today, the addition rule. Again, what we covered today, just like last time, it's sort of confusing, because on the addition rule, you got to be able to decide whether events are mutually exclusive or not mutually exclusive. Alright, mutually exclusive. When events are mutually exclusive, that means the two events cannot occur at the same time. Might be real beneficial to write that down. Two events can't occur at the same time. That's what mutually exclusive means. I drew these pictures here maybe to help you out. This is what two events look like if they're mutually exclusive. A and B are two separate bubbles and they don't intersect. Right? They don't share any possible outcomes. This A and B, they cross each other in our Venn diagram, so they share this part in here, so they're not mutually exclusive. They could happen at the same time. Just a quick example of mutually exclusive events. Two events, something like if we're rolling a die. If we're rolling a die and we want the probability that you get a 5 or a 6, getting a 5 and getting a 6, two completely separate events. They can't happen at the same time. All right, if we roll the die, we could get a 5 or we could get a 6, but you can't get a 5 and a 6 at the same time. Events that are not mutually exclusive might be something like rolling a 5 or rolling a odd number. Those are not mutually exclusive because if we roll a 5, we did both. Does that make sense? So mutually exclusive can't happen at the same time. Not mutually exclusive could happen at the same time. And that's just what this said, what I just said, so I'm just going to go on. Mutually exclusive, first event has one outcome, second event has one outcome, they can't happen together. If we picked a male, remember that problem we were doing last class where we had the nursing school? If we picked a male student and and we want them to be a nursing major, those two things could happen at the same time, so they're not mutually exclusive. Because you could have John that's a student at the school and he's a nursing major. So he would be in there both. The word and, if you see the word and, then you want both events to occur. So if you have A and B, probability of A and B, then we want both events to occur. If we see the word or, then we want the first event to occur, the second event to occur, or maybe both at the same time. So, two different things there. When you have the word and or the word or, it means different kinds of probabilities. Alright, probability A and B means you get A, then you get B. So you get both of them to happen. Probability of A or B means you get A or B. So something like this one, let's say probability that I pick a king and a queen from a deck of cards. Well, then apparently how many cards am I going to draw out of the deck? 2. All right. When I do this one down here, probability that I get a king or a queen. Now it looks like I'm going to draw how many times? Just one. So you got to be able to separate those things and know that they mean something different. Addition. Let's go ahead and write this down. This is pretty important. Matter of fact, I'll put up the whole slide. The addition rule. The addition rule, you have two different things. If the events are not mutually exclusive, then you have the top thing. If they are mutually exclusive, then you have the bottom formula. mutually exclusive events. Ms. Tomlin. Notice we're not multiplying them now. Because when we put the word or in there, it's like we're doing one pick. So we want either A or B to happen. On the other homework from the last time, we wanted A and B to happen. So those two, that's when we were using the multiplication rule. So notice on this one, it says, what you have to do, you have to find the probability. If they're not mutually exclusive, so if they could happen at the same time, you find the probability of the first event, probability of the second event, add those together, and then you gotta subtract off the probability that both events could occur at the same time. Down here, if they're mutually exclusive, then we don't have to worry about that last part because they can't occur at the same time. So all we have to do is just the probability of the first event plus the probability of the second event. And we'll do a couple of examples here that maybe will explain it a little better. Alright, so just to read this, probability of A or B, add the probabilities of the first event and the second event, then you subtract off the probability that the events could happen at the same time. Alright, so this is an example. You select a card from a standard deck. Find the probability that the card is a 4 or an ace. So we're looking at probability that you get a 4 or an ace. Are these events mutually exclusive or not mutually exclusive? Are they? I don't know, I'm asking. They're mutually exclusive, aren't they? Because if you draw a 4, can it also be an ace? So they can't happen at the same time. So all we have to do here is find the probability that you get a 4 and add it to the probability that you get an ace. What is the probability that you get a 4 out of a deck of cards? 4 out of 52 plus what's probability you get an ace if you draw? 4 out of 52. Notice we didn't change this to 51 this time because we're not doing two separate draws. We're not wanting to get a 4 and an ace. We're just saying you draw once and either you get a 4 or you get an ace. And all you gotta do is add those. 8 out of 52, and then you could use your calculator and change that into a decimal. Make sure we did this right. So we got 4 out of 52, 4 out of 52, which is 8 out of 52, comes out to be about 15% of the time that you're gonna get a 4 and an ace. Notice when they drew the bubbles here, mutually exclusive events. They can't both happen at the same time. You can't get a card that's a 4 and an ace at the same time. You roll a die, you find the probability of a number less than 3 or an odd number. So we want probability that you're less than 3 or an odd number. Are those mutually exclusive?
Yes.
No, because if you're less than 3, what are the numbers that are less than 3? Close. 1 and 2, right? 3, because we're not less than 3 there. What's all the odd numbers? 1, keep going.
Oh, all of them?
3 and 5. What do they share? They share the 1. So when we do this, what we have to do is we have to find the probability of getting a number less than 3, which is 2 out of 6, plus probability of getting an odd number, which is 3 out of 6, and then we got to subtract off the probability that they share. Well, how many numbers did they share? So the probability that you get that number is 1 out of 6, and then we just do the math. 2 plus 3 is 5, So 5 out of 6 minus 1 out of 6, which is 4 out of 6, which reduces to 2/3 or about 0.667. So that's an event that's not mutually exclusive. Not mutually exclusive. They share the 1 right here, so they're not mutually exclusive. Find the probability. We do what we just did there, 2/6 plus 3/6 minus 1/6. You get 4/6, which is a decimal is 0.667. Alright, frequency, this frequency distribution shows the volume of sales and the number of months of sales representative reached each sales level. Can't read. If this sales pattern continues, what is the probability that the sales rep will sell between 75,000 and 124,999? So we're in this range. How many people sold in that range? Or how many months was there? 16. You just add those two together, right? So 16 out of a total of how many months? How could we find the total? And remember when we were doing these frequency distributions, didn't we normally have this totaled up down here? Yeah. And it's 36, so our probability should be 16 out of 36. Let's see if we did it right. So we're looking at those two. Are those mutually exclusive events, or could they both happen at the same time? Could one salesperson for 1 month be at 80,000 and at 110,000? No, it's not possible, is it? Either they're at one or they're at the other. So mutually exclusive. So all we do is take the 7 out of 36 plus the 9 out of 36 and get 16 out of 36. 0.444. Next one, a little tougher on this one. Blood bank catalogs the types of bloods. Well, no, this one's not tough. You got a donor is selected at random. Find the probability that they have type O or type A. So we want a probability of O or A. Let's just figure this one real quick. What's the probability that a donor has type O blood? Where can we find how many people have type O blood?
184.
184 right here. So that's 184 out of the total 409. Now the type O and type A, are they mutually exclusive, or could that one person have both type O and type A blood? It's not possible, is it? So they're mutually exclusive. So all we got to do is add on the other one. What's the probability you get type A?
164.
164 out of 409. You add those two together and you get 348 out of 409. Change that to a decimal, whatever it comes out to be. That's going to be our answer. Mutually exclusive events. Let's see if we did it right. 348 out of 409, is that what we said?
Yeah.
Sorry. Next one, a little tougher on this one. This time we want probability that you have a donor type B or an RH negative. So let's do the probability of type B. What's the probability that somebody has type B blood? 45 out of 409. Plus, what's the probability that they have RH negative? 65 out of 409. Are those mutually exclusive events or not mutually exclusive? They're not, because these 8 people right here have RH negative and type B blood, right? So what we have to do is subtract those 8 people off. 8 out of that 409. 45 plus that's 110. 110 minus 8 is 102 out of 409. We change that to a decimal, and that should be our answer.
That isn't that hard.
It's not really that hard. You just got to think it through. So 102 out of 409 is what we said, about 25%. Alright, this is just showing all the stuff that we've covered with probabilities. Classical probability, remember classical probability? Total, or favorable outcomes over total outcomes. Empirical probability. Remember, empirical is when we did some kind of experiment, like with the M&Ms at the very start of the year. Range of probabilities rule. We know that probabilities always got to fall between what two numbers? 0 and 1 or 100 if you're doing percents. So it's always got to be from 0 to 1. What if the probability is 0? It's never going to happen. What if it's 1? It's going to happen every single time. I wonder why it's making, when I'm drawing here, it's making it like a polygon, isn't it? I wonder why. Complementary events. Remember, to find the complement of an event, you subtract from 1. Multiplication rule. We use the multiplication rule when we see the word what? And. You might want to write that down somewhere. When you see and, you're multiplying. When you see or, what are you going to be doing instead of multiplying? You're adding. Alright? So two different things there. You got to make sure you keep those separate and know that they're two different things. Alright, that's your assignment, page 161.
Oh, wow. Goodness. I love you. Give me don't do it though.
That's alright, I remember last year, this time, people sitting in here laughing about not doing their homework, and then those same people were, in May, were in here going, I'm not gonna graduate. And I was going, good.
You're on the recording, man.
I don't care.
You
Not like I'm lying. Do you think I weren't laughing at those people last year when they screwed around, and
I bet you cut that out.
that I don't, 'cause I don't know how. You think if Mr. McKnight walked in here, I would tell him any different? No, when Mr. Fisher came in last year and said, well, you got these 4 people that are awful close, they're probably not gonna graduate because prop stats, what are we gonna do about it? And I said,
You scared Mr. Fisher away.
I said, I ain't gonna do nothing about it. I said, they better do something about it, and they should have did something about it back at the start of the year so that they didn't have to worry about it now.
And that's why I left.
Which ones they have on here, or which ones I put on here worked out. Let's, problem 14, problem 20, and problem 24, let's try those. 14, 20, that way we can check, see, oops, that way we can check, see if we do them right, because I already have them on the PowerPoint worked out.
I can check if you want.
No, you've never seen that book again. Problem 14. Just because that's one of them that I think was hard. So I put it on the PowerPoint. 14, 20, and what'd I say? 14, 20, and what? 24?
Elementary.
But it's definitely on there.
Oh. Guys, just make sure you keep listening to Dalton because the tests are on there also.
What?
I'm lying. I'm being sarcastic because Hunter's on all the homeworks. We'll get you into that in May. Because then your test will be like 20s and 30s. But if you just copy answers from something else, then. Problem 14. Math conference has an attendance of 4,950 people. Of these, 2,110 people are college professors, and 2,575 are females. Of the college professors, 960 are females. Are the events of selecting a female and selecting a college professor mutually exclusive. So we want selecting a female or a professor. Can those two things happen at the same time?
Yes.
Yeah.
Only in Jesse's world, where he's a sexist pig, can they not happen at the same time? Because can a college professor be a female now?
Yeah.
Yeah, Jesse's still living back in the 1800s, right, where females weren't allowed to do stuff like that. So this is not mutually exclusive. They're not mutually exclusive. Because they could happen at the same time. Letter 14, the conference selects people at random to win prizes. Find the probability that a selected person is female or a college professor. So we want female or a professor. We did it, but we just told that it was mutually exclusive or not. Now we're actually finding the probability. First thing we're going to do is find the probability that they're a female. How many total people were at this conference?
49, 50,
And how many of them were female?
960.
Is that right, 960? Be careful on this, because I think they gave us two different female numbers, right?
Oh no, it's 25. 75.
How many people? So 25, 75 were female, right? Total females. Plus, now we do the professors. How many professors were at this conference?
2110.
And that's out of the 4950 again. Now, since these are not mutually exclusive events, what Jacob was thinking of a second ago, we gotta subtract that off, because we've included some of these people in there twice. So we gotta subtract off, and the ones we gotta subtract off are the ones that are female and a professor. So how many female professors were there?
960.
That's out of 4950. So what do we get here? We got 4,685. 4,685 minus, somebody help me out with the calculator, so I don't have to try to do this in my head. What's 4685 minus 960? Now we want to change that to a decimal, so take 3725 divided by 4950.
47,525.
So about 0.753. About 75% of the people there were female or a professor. Everybody have that one? Not too difficult, right? Jacob, you can handle that, right? That's pretty easy. Just gotta think. You really gotta think, okay? Are they mutually exclusive, not mutually exclusive? And do I have to subtract off something here at the end? And you gotta be real careful, because when we get to the test over this stuff, if that says or in there, you do one thing. If it says and in there, you do something completely different. All right, look at problem 20. Tacoma Narrows Bridge. Anybody know what the Tacoma Narrows Bridge is? Bet you've seen it before. Washington.
I've never been to Washington.
You didn't have to go to Washington to see it. Why is the Tacoma Narrows Bridge famous?
It's narrow.
The Narrows is the water that it goes over, that's what it's called. So write this down. Tacoma Narrows Bridge. Yeah, because all car names come before the actual words are made up. There wasn't no such thing as a Bronco out in the world until GM made the Bronco. Wasn't no such thing as a Mustang until Ford made the Mustang. And then they start calling the horse, oh yeah, we'll call this a Mustang.
It's just as fast.
If you look up and figure out next time, if somebody tells me, I'll give you a free homework grade. So if you can, don't even get nothing out now. So until 8:52, nothing counts. You get your phone out, I'll take it away, and then you'll have it missing all day. The present distribution, the percent distribution of number of occupants and vehicles crossing the Tacoma Narrows Bridge in Washington is shown in the pie chart. Find each probability. Letter A. Randomly selecting a car with 2 occupants. So we want the probability that the car has 2 occupants in it. Where are we going to find that at? Looking at your pie charts up there. Or actually, you're only looking at one of them. It tells you underneath which one you're looking at. Say it again. 29.8%. So all we really got to write is 0.298. They gave us all the percentages. This time we don't even have to. We didn't have to do anything on that one. Randomly selecting a car with 2 or more occupants in it. 2 or more. How are we going to find that? Alright, so we want 2 or more. So you could, 2 or more, you could add up all the ones that are 2, 3, 4, 5, and 6 or more, right? What's it come out to be? So 0.445. Is there another way you could find that?
You could subtract 1 from 55.5.
We should be able to say, if we want 2 or more, then that means 1, not 1 or less, because only somebody like Dalton would have a car that has no occupants in it, right? So we could just take the 1, which is 55.5, and subtract that off. Do we get the same number? Yeah. So either way would have worked there. Could have found the complement, or you could have added them up like we just did. Letter C, randomly selecting a car with between 2 and 5 occupants inclusive. Anybody know what that means, inclusive? 2 to 5 inclusive. What's that mean? Are we including 2? Yeah, that's what inclusive means. It means you're including 2 and you're including 5. How are we going to find that? Add up what? Probability 2 plus probability of 3 plus probability of 4 plus probability of 5. Now, are these events mutually exclusive? Is there something that we need to subtract off out here at the end? Is there a car that's going to have 3 people in it and 5 people in it? No. So they're mutually exclusive, so all we got to do is add those up. What you come up with?
Isn't it
43.5. So 0.435. If you left them as a percent, that would be okay. I changed all of them to decimal form because that's what this book does for whatever reason, even though they gave you the percents to begin with. was the other problem? 24, is that the other one I said? If you see one that you want to work, it's on the assignment, tell me here in a minute. 24 left-handed people in a sample of 1,000 people, 525 men, 475 women, 113 are left-handed, 63 men, 50 women. They give us all this down that chart right there. The results of the sample are shown in the table. A person is selected at random from the sample. Find the probability of each event. So 24, part A. What's the probability they want in part A?
Left-handed or female.
Left or female. Are these two mutually exclusive or not mutually exclusive? Not mutually exclusive. So that means when we do this, we're gonna have to subtract something off out here at the end. We're going probability of one plus probability of the other minus probability that both of them occur. What's probability the person's left-handed if we pick from that? 113 out of 1,000, good. What's probability that person's a female?
That would be
475 out of 1,000. Now, we gotta subtract off the probability that they're left-handed and a female. So what's that out of 1,000? How many left-handed females were there in the 50? So we do all that, that's what, 588? 588 minus 50 is 538 out of 1,000. Divide that. Don't really need your calculator because if you divide by 1,000, you just move the decimal over 3 places, so 0.538. Does that seem right?
Yeah.
Letter B. Person's right-handed or male. So you got a right-handed person or a male. Mutually exclusive or not mutually exclusive?
It is.
Are they mutually exclusive?
No, no.
They're not,
It's
are
like
they?
backwards. It's hard to, you have to
Yeah.
think about it.
So what's the chance of getting a right-handed person? What is it? 887 out of 1,000. What's the chance of getting a male?
125.
That's out of 1,000. Then we want to subtract off what's the probability of getting a right-handed person that is a male. 462
Yeah.
out of 1,000. So we got 1,412. 1,412 minus 462. What is that? About 990? Is that right? No. 1,412. 950. So 950 out of 1,000. Bump our decimal over 3 places. 0.95%. Or 0.95, not 95%. Either 95% or 0.95. Does that make sense?
Yeah.
That don't seem right, does it? Doesn't that seem awful high? How come it's high?
Right-handed males.
Okay, we're looking at right-handed. That's gonna be most of the people, right?
Yeah.
So it should be a pretty high number.
Makes sense.
So, makes sense this time. Letter C, what's it say? So, not right-handed? Or what? Male? So we want all the people that are not right-handed or a male. We're gonna find the people that's not right-handed. They didn't tell us that. Or did they tell us that?
Is that the just left-handed?
So that'd be the left-handed people, wouldn't it? So not right-handed this time would just be the left-handed people. Or you could just say it's the complement of this that we just did, which is 113 out of 1,000. What's probability of male? We just did that one, didn't we? 525 out of 1,000. Now, are those mutually exclusive?
No.
No. What are they gonna share this time? What people they gonna share? Not right-handed male means that the person is a left-handed male, right? So, how many left-handed males did we have?
I thought it was not.
63.
I understand. 63 out of 1,000. Gotta subtract that off. That's 638 minus 63. 638 minus 63 and 587, is that right? No. 585?
Yeah.
585? You guys aren't just agreeing with me because I'm a math teacher, right?
No, that's right.
Alright, so 0.585 would be our decimal. What letter D say?
Person is right-handed and
And is a male?
is female.
All female. Is it different this time?
Yeah.
So this time all we're gonna do, we want both events to happen this time because we got the and in there. Alright, so how many right-handed females do we have? 425 out of a total of 1,000. That should be all we have to do, divide that and get 0.425. Letter E. Letter E says, are the events being right-handed and being female mutually exclusive? We already talked about that. Are they mutually exclusive?
I didn't get the last one.
It just erased on me. I don't know what happened. Letter E, are they mutually exclusive? No, you can be right-handed and a female at the same time. Somebody help Jesse out and tell him what that last one was. The letter D. It was like
0.425.
0.425.